A lot of physicists before Bohr had tried to analyze the structure of an atom, but only managed to get part of the picture. Kirchhoff found out that particular elements radiated light in separate wavelengths, so the spectrum that consisted of a number of bright lines separated by stretches of darkness. The elements present in a particular mineral can be identified by the wavelengths emitted when the mineral was strongly heated. Still, no one knew why different elements radiated or absorbed different wavelengths. Particularly interested in the spectrum of glowing hydrogen simpler than other elements was Swiss physicist Johann Jacob Balmer, who made a further development in the puzzle.
Yeah.
So you can tell what an element is based on the number of spectral lines in the spectroscope.
Hydrogen's spectrum consisted of a series of lines spaced more and more closely with decreasing wavelengths. In 1885, Balmer discovered a formula for the wavelengths of these lines. The formula included a symbol that could be replaced with successive square numbers, and as a result, the successive wavelengths of the lines in the hydrogen spectrum could be determined. Balmer's consistency in the lines that somehow must be related to the structure of an atom. However, it still did not explain why the lines were where they were. Finally, we get to Niels Bohr. Niels Bohr insisted that as long as an electron remained in orbit, it did not radiate energy. However, when hydrogen was heated, it did radiate electricity, and when cooled, it absorbed it. Wavelengths emitted fit Balmer's equation, and to explain this, Bohr thought that the electron in the hydrogen atom could be in any number of different orbits with different distances from the nucleus. Whenever it was in a particular orbit, it would not gain or lose energy. It was in fact the change in orbits that did so. If it moved away from the nucleus, it absorbed energy. If it moved closer, it emitted energy. Bohr questioned why an element in a particular orbit would suddenly change orbits, never stopping in an orbit in between the two. He hypothesized that it would have something to do with quantum theory.
I hypothesize this has to do with quantum physics.
Quantum physics theory consists of 5 main ideas. The first one is that energy is not ongoing and comes in small units. The second one is that the elementary particles act like particles in waves. The third is movement of particles are randomly done. The fourth is it is not possible to know the movement and position of particles at the same time. And the last one is that the atomic world is nothing like the world we live in. And that because there are different levels of energy, an atom can only absorb visible light of a certain wavelength.
If the atom could only handle quanta of a certain size, it could only absorb light of a certain wavelength, and an electron would be sent into the next orbit. Bohr worked out a series of calculations showing a series of orbits that would result in the absorption or emission of quanta of fixed size, and that would account for the particular wavelength of the lines in the hydrogen spectrum.
Bohr's conclusion is illustrated here. The electrons in the atom are shown in the first energy level. One electron gains more energy and shoots out to the second energy level and becomes more excited. When the electron's energy is decreased, the electron releases energy in the form of a photon, which can be seen as visible light. In the second illustration of Bohr's theory, the electrons again are shown in the first energy level. Again, as the electron gains energy, it shoots out to the third energy level because it gained more energy than the time it shot out to the second energy level. As the energy from the electron releases, a yellow photon is released. We're good. Go.
Hi, I'm Niels Bohr. I'm introducing to you the model I created based on the experiment I conducted. It concluded that atoms have different energy levels. When an electron in the ground state gains energy, it is moved into the excited state. Then when it loses that energy, it's released as a photon in the form of visible light. The further the electron moves from the excited state to the ground state, the more energy is released, and the higher frequency the visible light released will be.
Bohr received the Nobel Prize in 1922 for this work, showing that the structure of the atom could not be figured according to the classical physics, but by using the quantum theory. Bohr's formula gave the figures for the wavelengths of the spectral lines. However, as the spectral lines were studied with increasingly refined instruments, it was seen that each line was actually a number of closely spaced thinner lines, as if Bohr's orbits consisted of a family of orbits with very small differences among them.
Bohr's work left questions. German physicist Arnold Sommerfeld pointed out that orbits represented by Bohr as a circular might be elliptical and in different degrees. Bohr's original quantum number, the number inserted in the formula representing a set of spectral lines, has to be a whole number greater than 1. However, Sommerfeld's quantum number could be 0. With these two quantum numbers, the fine structure of the spectral lines could be expressed. Eventually, a third quantum number following for 3 negative dimensional orbits was discovered. This was called the magnetic quantum number. Furthermore, physicist Wolfgang Pauli determined a fourth quantum number representing the spin of the electron either clockwise or counterclockwise on its axis. Bohr's work led people to question why an electron in orbit doesn't radiate as well as why it can only emit quanta of a certain size. Physicists such as Wiener or Heisenberg continued Bohr's work, elaborating on these points.